Hello there, and welcome. It's good that you're here. Perhaps you've had a long day, or perhaps you're simply the kind of person who finds comfort in understanding how the world around you works. Either way, tonight's journey is just for you. You have nothing to do but rest. Let your breathing slow, your shoulders drop, and your mind drift gently along as we explore something you've used thousands of times without a second thought. Tonight, we're going to discover how zippers work, not in a technical, jarring way, but slowly, peacefully, the way you might watch clouds drift across an afternoon sky. We'll trace the gentle clicking of those tiny metal teeth as they lock together, one after another, in a dance that's been perfected over more than a century. We'll feel the smooth glide of the slider as it brings two separate pieces together into one continuous seal. And we'll understand, in the quietest possible way, why this simple device has become one of the most reliable fasteners ever invented. Zippers are everywhere. On your jacket right now, perhaps. On the bag you carried today. On the case that holds your pillow. They're so common, so dependable, that we rarely think about them until one breaks or gets stuck. But tonight, as you settle into comfort, we're going to think about them differently. We're going to appreciate the gentle engineering, the careful thought, and the quiet precision that makes a zipper work perfectly. Time after time, thousands of times over a lifetime. A zipper is essentially a mechanical marvel hiding in plain sight. At its most basic, it's two strips of fabric tape, each lined with dozens or even hundreds of tiny teeth. These teeth are shaped just so, with curves and hollows and projections that fit together in one specific way. Between them sits a slider, a small metal or plastic device with a Y-shaped channel running through its center. When you pull the slider upward, it guides these teeth together at just the right angle, and they lock into place, one pair after another, until the two separate pieces of fabric become joined as one continuous seam. When you pull the slider downward, a wedge inside it gently pries the teeth apart again, and the seam opens. That's the overview, the bird's eye view. But oh, there's so much more to discover in the details. There's the careful geometry of each tooth, designed so precisely that forces trying to pull the zipper apart from the side cannot separate them. There's the spring-like quality of the materials, which allows the teeth to flex just enough to lock together, but never so much that they deform permanently. There's the friction-reducing coating that lets the slider glide smoothly without catching. There's the tape itself, woven with specific thread counts to hold the teeth firmly while remaining flexible enough to curve around your body or fold into a bag. And there's the history, too. The long, patient history of inventors who dreamed of easier ways to fasten clothing, who failed again and again, who refined and tested and persevered until finally, in the early decades of the 20th century, they created something that worked beautifully. Something that would go on to fasten billions of garments, bags, and devices around the world. Tonight, we'll walk through all of this together, gently and without rush. We'll start at the beginning, in a time before zippers existed, when people struggled with long rows of tiny buttons and tangled bootlaces. We'll meet the inventors who imagined something better. We'll watch as their ideas evolved from clumsy, unreliable mechanisms into the smooth, dependable fasteners we use today. We'll look closely at the teeth themselves, understanding their shape and the forces that hold them together. We'll explore the different materials from which zippers are made, from gleaming brass to lightweight nylon to flexible coils of plastic. We'll visit in our minds the factories where millions of zippers are manufactured each day, and we'll discover the quiet companies that have perfected this craft over decades. By the end of our journey tonight, you'll never look at a zipper quite the same way again. You'll see the engineering in the everyday. You'll appreciate the thought and care that went into something so small. And perhaps as you drift toward sleep, you'll feel a gentle satisfaction in understanding one more small piece of the intricate world we live in. So let's begin. Let your eyes grow heavy if they wish. Let your body sink deeper into comfort. And let's travel back in time to an era before zippers to understand why someone felt the need to invent them in the first place. Imagine for a moment that you're getting dressed on a cold morning in the year 1850. You're not reaching for a jacket with a simple zipper that closes with one smooth pull. Instead, you're facing a row of 15 or 20 small buttons, each one needing to be carefully threaded through its buttonhole. If you're wearing fashionable boots, you might be dealing with even more buttons, perhaps 30 or 40 running up the side of each boot. Your fingers are cold. The buttons are small. Some of them slip through your fingers. One of the buttonholes is frayed, making it even harder to push the button through. This was the daily reality for millions of people in the 19th century. Buttons had been around for thousands of years, and they worked well enough, but they were slow. They required 2 hands, careful attention, and a fair amount of dexterity. For elderly people, or those with arthritis, buttoning a long row of fasteners could be genuinely difficult. For children learning to dress themselves, it was a frustrating challenge. And for anyone in a hurry, well, there simply wasn't a way to fasten clothing quickly. Laces were another option, especially for boots and corsets. These had their own challenges. They needed to be threaded carefully, tied securely, and adjusted to the right tension. They came untied at inconvenient moments. They tangled, they frayed and broke, and like buttons, they were slow. Hooks and eyes offered another alternative. These small metal fasteners consisted of a hook on one side and a loop or eye on the other. They were faster than buttons, but they still required careful alignment and could be fiddly to work with, especially when there were many of them in a row. They also had a tendency to catch on fabric or come undone if stressed. All of these fastening methods shared a common limitation. They were discrete. Each button was separate from the next. Each hook was independent. There was no continuous fastening that could be opened or closed all at once. This meant that if you wanted to open a garment quickly, you had to undo each individual fastener, one by one. And if you wanted it to close again, you had to reverse the process, carefully aligning and fastening each piece. It was this fundamental limitation that sparked the imagination of inventors in the mid-1800s. What if, they wondered, there could be a continuous fastener? What if you could close an entire opening with a single motion? What if dozens of small fastening points could all be operated at once, smoothly and reliably? This question floated in the minds of creative people for decades. It seemed like it should be possible after all, if you could create a mechanism that joined things together point by point, And if you could design it so that one action affected all the points simultaneously, then you'd have something revolutionary. Something that could transform how people dressed, how bags were secured, how tents were sealed. The applications seemed endless. But transforming that idea into reality proved extraordinarily difficult. The mechanism needed to be reliable. It needed to work every single time. It needed to be small enough to be practical, strong enough to withstand tension, and simple enough to be manufactured affordably. And it needed to be something people would actually want to use. Something that felt better than the familiar buttons and laces they'd grown up with. The first person to really try to solve this puzzle was a man named Elias Howe, Jr. You might recognize his name. He's better known for inventing the sewing machine, a device that revolutionized textile manufacturing in the mid-1800s. But in 1851, Howe received a patent for something he called an automatic continuous clothing closure. It was an early ancestor of the zipper. Howe's device consisted of a series of clasps that were united by a connecting cord. This cord would run or slide upon ribs, and as it moved, it would bring the clasps together or pull them apart. The idea was sound in principle. It was a continuous fastener that could be operated with a single motion. But it had problems. The mechanism was complicated. It was difficult to manufacture. And most importantly, it didn't work very reliably. The clasps had a tendency to jam or come undone at awkward moments. Perhaps discouraged by these difficulties, or perhaps simply because his sewing machine business was going so well, Howe never seriously tried to market his automatic closure. He let the patent sit unused, a promising idea that never quite made it into the world. And so the patent expired, the design was forgotten, and people continued to button their boots every morning with patient fingers. It would be more than 40 years before another inventor took up the challenge. By then, it was the 1890s. The world was changing rapidly. Electricity was beginning to light cities. Telephones connected people across distances. Automobiles were being experimented with. It was an age of invention, of mechanical ingenuity, of solving problems with clever engineering. And one inventor, frustrated with his own daily struggle with boot buttons, decided to try again where Elias Howe had left off. His name was Whitcomb L. Judson, and unlike Howe, he would dedicate years of his life to perfecting a slide fastener. He would face failure after failure, create design after design, and spend enormous amounts of time and money pursuing his vision. And while his designs never quite succeeded during his lifetime, they would lay the groundwork for someone else to finally solve the puzzle. So let's meet Whitcomb Judson and follow his patient, frustrating journey toward the creation of something that would eventually become indispensable to the modern world. Whitcomb Leonard Judson was born in 1843 in Chicago, Illinois. He served in the Union Army during the American Civil War and afterward established himself as a mechanical engineer and inventor. He was a creative man with a restless mind, always looking for mechanical solutions to everyday problems. Over the course of his career, he would receive 30 patents covering everything from pneumatic street railway systems to motor mechanisms. But the invention he's remembered for, the one that would eventually change the world, started with a very personal frustration. According to some accounts, Judson may have been inspired by a friend who suffered from a bad back and found it difficult to bend over to lace boots. While this story appears in various historical narratives, what we know for certain is that Judson, like many inventors of his era, was looking for ways to improve upon existing fastening methods. High-button boots were fashionable at the time, and fastening them was indeed tedious work, requiring patience and dexterity. Whether motivated by a friend's struggle or simply by the universal inconvenience of the era's footwear, Judson began to envision a better way to fasten boots with a single, simple motion. Judson began sketching ideas. He experimented with different mechanisms. And in November 1891, he filed his first patent application for what he called a clasp locker. It was a device designed specifically for fastening shoes and boots, though Judson believed it could be applied to other garments as well. The clasp locker was, in principle, quite clever. It consisted of 2 rows of interlocking hooks and eyes, each hook designed to catch into a corresponding eye on the opposite side. Between these rows was a slide mechanism, a kind of guide that would pull the hooks and eyes together as it moved up, and separate them as it moved down. If you pulled the slide up from the bottom of the boot to the top, all the hooks would engage with all the eyes, and your boot would be fastened. If you pulled it down, they would all disengage, and you could step out of your boot easily. On paper, it was exactly what was needed: a continuous fastener, quick to operate, no more lacing, no more bending over. Judson was excited about his invention. He refined the design and actually filed for a second, improved patent before the first one was even approved. Both patents were eventually issued on the same day, August 29, 1893. Patent numbers 504,038 and 504,037, if you're curious. They sit in the archives now, pieces of history, their careful diagrams showing rows of hooks and guides and sliding mechanisms. Judson was confident enough in his invention that he decided to debut it publicly at the 1893 Chicago World's Fair, also known as the World's Columbian Exposition. This was one of the grandest exhibitions of its time, showcasing innovations from around the world. Millions of people attended. It seemed like the perfect place to introduce a revolutionary new fastener to the public. At the fair, Judson displayed his clasp locker, explaining how it worked, demonstrating its operation. He had models that visitors could try. He had promotional materials. He was convinced that people would immediately see the value of his invention and that orders would pour in. But they didn't. The public's response was lukewarm at best. Some people were intrigued, certainly. The idea was novel. But when people actually tried to use the clasp locker, they encountered problems. Sometimes the hooks wouldn't engage properly. Sometimes they would pop open unexpectedly when stress was applied. Sometimes the slide would jam, requiring fiddling and frustration to get it moving again. The device was unreliable, and reliability was exactly what a fastener needed most. Still, Judson believed in his invention. He found investors, including a businessman named Lewis Walker, who would become his long-term partner. Together, they founded the Universal Fastener Company in 1894 to manufacture and sell the clasp locker. They set up production. They marketed the device. And they waited for success. It didn't come. Over the next several years, Judson created variation after variation of his design. He adjusted the shape of the hooks. He changed the guide mechanism. He tried different materials. Each new version promised to fix the problems of the previous one. But each new version still had issues. They were difficult to manufacture consistently. They were prone to jamming. They were unreliable in ways that made them unsuitable for everyday use. The company struggled. They made some sales, mostly to industrial applications, where the occasional jam wasn't catastrophic. But they never achieved the widespread adoption that Judson had dreamed of. The boot market remained largely uninterested. Clothing manufacturers didn't want to take a chance on an unreliable fastener, and consumers, when given the choice, stuck with their familiar buttons and laces. This must have been deeply frustrating for Judson. He could see so clearly what his invention should be. He could envision how useful it would be if only he could get it to work reliably. But the gap between vision and reality proved stubbornly difficult to close. He spent years of his life and considerable amounts of money pursuing this goal, and he died in 1909 without ever seeing his dream fully realized. But his work wasn't wasted. Far from it, because Judson's company, the Universal Fastener Company, would eventually hire someone who could solve the problems that had stymied Judson for so long. Someone who would take the basic concept of a slide fastener, reimagine it completely, and create a design that actually worked. That person was Gideon Sundback, and it's time we met him. Gideon Sundback was born on April 24, 1880, in a small farming community in Sweden. His parents, Jonas Otto Magnusson Sundback and Christina Carolina Klasdotter, raised him in a modest but hard-working household. Young Gideon showed an early aptitude for mechanical things, and when he was old enough, he pursued formal education in engineering. He attended a polytechnic school in Germany, where he immersed himself in the principles of mechanical design, mathematics, and manufacturing. In 1903, Sundback passed his engineering exam, officially becoming a qualified engineer. But opportunities in Sweden and Germany seemed limited, and like many young Europeans at the turn of the 20th century, Sundback set his sights on America, a land of industrial growth and opportunity. In 1905, at the age of 25, he emigrated to the United States, ready to apply his skills in this new world. His timing was fortunate. In 1906, he was hired by the Universal Fastener Company, the same company that Whitcomb Judson had founded. The company, still struggling to make Judson's clasp locker work properly, was looking for skilled engineers who might be able to improve the design. Sundback, with his fresh perspective and solid engineering training, seemed like a promising candidate. Sundback proved himself quickly. He was methodical, patient, and possessed a deep understanding of how mechanical systems should work. Within a year of joining the company, he was promoted to head designer. And it was in this role that he began to seriously wrestle with the fundamental problem. How do you create a continuous slide fastener that works reliably? Sundback's early efforts followed the same path that Judson had taken. He worked on improving the hook and eye design, adjusting the shapes, refining the mechanisms. In 1909, he created a design called the Placo fastener, which was seen as an improvement over Judson's original. The patent for this design was actually filed under Judson's name, as was common practice at the time. Companies often kept patents in the founder's name, regardless of who had actually done the design work. But even the Placo fastener wasn't good enough. It was still prone to the same problems that had plagued earlier versions. Sundback knew there had to be a better approach. He began to think more radically. Maybe the problem wasn't just in the details of the hook and eye design. Maybe the fundamental concept needed to be reconsidered. Then, in 1911, Sundback experienced a personal tragedy when his wife, Elvira Aronson, died suddenly. According to company histories and biographical accounts, the grief-stricken Sundback channeled his emotions into his work, spending long hours at the drawing board and in the workshop. Whether the intensity of this personal loss directly influenced his breakthrough is difficult to say with certainty, but it was during this period of intense focus that he finally made the leap forward that had eluded others. The key insight was this: instead of trying to perfect a hook and eye design, why not create something entirely different? Why not design teeth that were symmetrical? Teeth that could interlock directly with each other, rather than relying on separate hooks and eyes? And why not make these teeth small, much smaller than earlier designs, so that there would be more of them per inch, creating a stronger, more secure closure? In 1913, Sundback filed a patent for what he called the hookless fastener No. 1. This design increased the number of fastening elements from 4 per inch, which was typical of earlier designs, to 10 or even 11 per inch. That's one tooth approximately every 2.5 millimeters. With so many more teeth, the fastener was much stronger and more secure. But the real innovation was in the shape of the teeth themselves. Sundback designed them with cup-shaped hollows on one side and rounded projections on the other. When the slider brought 2 teeth together, the projection on one tooth would nestle into the hollow of the tooth opposite it. This created a kind of socket joint, a stable configuration where the teeth literally fit together like pieces of a puzzle. Furthermore, Sundback designed the teeth so that they would be slightly offset from each other. This meant that as the slider brought them together, each tooth would engage in sequence, one after another in a graceful wave of interlocking. This sequential engagement distributed the forces evenly and made the fastener much smoother to operate. The patent for the hookless fastener No. 1 was granted on April 29, 1913. This date would later be designated as National Zipper Day, though the device wasn't called a zipper yet. That name would come later. Sundback didn't stop there. He continued to refine his design, and in 1917 he filed another patent for what became known as the separable fastener. This version had all the improvements of the 1913 design, plus additional innovations that made it even more reliable and easier to manufacture. This 1917 design is essentially what we would recognize today as a modern zipper. But having a good design was only half the battle. The other half was manufacturing. It was one thing to create a working prototype in a workshop. It was quite another to produce thousands or millions of these fasteners consistently, affordably, and quickly. This is where Sundback's engineering brilliance truly showed. He invented a machine to manufacture his fasteners. This machine, which came to be known as the SL machine or the strapless machine, was a marvel of automated precision. It took a special Y-shaped wire as its input. The machine would cut small scoops from this wire, punch dimples into each scoop to create the cup shape, and then clamp each finished tooth onto a cloth tape in exactly the right position. All of this happened automatically, with the machine producing a continuous chain of interlocked teeth, one after another, at a remarkable speed. When the SL machine was first put into operation, it could produce several hundred feet of zipper per day. This was far faster than anything that had been achieved before. And because the machine did the work automatically, the quality was consistent. Each tooth was exactly the same size and shape. Each was positioned at exactly the right spacing. The fasteners that came off this machine actually worked reliably, time after time. Sundback's design, combined with his manufacturing innovation, finally solved the puzzle that had eluded Judson for so long. The Universal Fastener Company now had a product that was genuinely useful, genuinely reliable, and genuinely manufacturable at scale. All they needed now was for the world to adopt it. At first, adoption was slow. The general public was still wary after years of unreliable fasteners. But then came World War I, and with it, a need for practical, reliable equipment. The U.S. military saw the potential of Sundback's fasteners. In 1918, the Navy ordered 10,000 fasteners for use in flying suits. They were faster to put on than suits with buttons, and they stayed closed reliably even in the harsh conditions of early military aviation. Life vests also began using them. Money belts for soldiers adopted them. The military's endorsement gave the fastener credibility. After the war, civilian applications began to emerge. Tobacco pouches were an early success. The fastener kept the tobacco sealed and fresh. But the big breakthrough came in the 1920s when the B.F. Goodrich Company decided to use Sundback's fasteners on a new line of rubber galoshes. These waterproof boots were designed to be pulled on quickly over regular shoes to protect them from rain and snow. The distinctive zip sound that the fastener made when closing caught the attention of Goodrich's marketing team. In 1923, they decided to market the boots as zipper boots, with the word zipper evoking the sound of the fastener closing. The name was catchy, memorable, and onomatopoetic. It sounded like what it described. And it stuck. The public responded to the catchy name. People started calling the fastener itself a zipper, not just the boots. The word was too perfect, too natural to be used any other way. By the early 1920s, zipper was becoming the common term for Sundback's slide fasteners, and the name has remained ever since. From there, adoption grew steadily. In the 1930s, children's clothing manufacturers began using zippers, appreciating how much easier they made it for young children to dress themselves. In 1937, the zipper achieved a major milestone when it began appearing on men's trousers, replacing the button fly. This was sometimes called the Battle of the Fly, and the zipper won decisively. Fashion designers in Europe began incorporating zippers into their designs, appreciating both their functionality and their sleek, modern look. By the time Gideon Sundback died in 1954, zippers were everywhere. They were on jackets and pants, bags and luggage, tents and sleeping bags. The device that he had perfected had become one of the most common fasteners in the world. In 2006, more than 50 years after his death, Sundback was inducted into the National Inventors Hall of Fame, finally receiving recognition for his pivotal role in creating an indispensable part of modern life. But to truly appreciate what Sundback achieved, we need to understand how a zipper actually works. We need to look closely at those tiny teeth, examine the slider, and understand the gentle physics that makes it all come together. So let's slow down even more now and explore the anatomy of a zipper in peaceful detail. Imagine you're holding a jacket in your hands. Your fingers find the zipper pull, that small metal tab that you'll use to close the jacket. You give it a gentle tug, and the zipper begins to close, the two sides of the jacket coming together smoothly and securely. It happens so easily that you barely think about it. But in that simple motion, several different components are working together in carefully designed harmony. Let's examine each of them, one by one, understanding what they are and how they contribute to the zipper's operation. The first component, and perhaps the most important, is the teeth. These are also sometimes called elements. The teeth are the interlocking parts that actually hold the zipper closed. On a typical zipper, you might have hundreds of teeth, all lined up in perfect rows on each side of the zipper tape. The teeth can be made from different materials depending on the type of zipper, but they all share certain characteristics. Each tooth has a distinctive shape, carefully designed so that it can lock securely with a tooth from the opposite side. In metal zippers, each tooth is a separate piece, stamped from brass or aluminum or nickel, then crimped onto the tape. In plastic zippers, the teeth might be molded directly onto the tape, or they might be part of a continuous coil of nylon that winds its way along the tape's edge. Regardless of the material, the key feature of each tooth is its geometry. Each tooth has a rounded projection on one side and a corresponding hollow or cup on the other side. When two teeth come together, the projection from one nestles into the hollow of the other, creating a connection that's stable and secure. The teeth are also slightly offset from each other on the two sides of the zipper, which allows them to interlock in an overlapping pattern, like fingers interlaced in prayer. The shape of these teeth is crucial. They need to be designed so that they can flex slightly to allow engagement, but they need to spring back to their original shape once connected. This elastic quality prevents the teeth from deforming over time. The teeth also need to be shaped so that forces trying to pull the zipper apart from the sides cannot separate them. Only a very specific force, applied in a specific direction by the slider, can unlock them. Next, we have the tape. This is the fabric strip that runs along each side of the zipper, and it's what gets sewn into your jacket or bag. The tape serves as the foundation for the entire zipper, holding the teeth in place and providing a stable structure. Zipper tape is typically made from woven fabric, most commonly cotton, polyester, or a blend of both. Polyester has become the standard for most applications because it's strong, doesn't shrink when washed, and resists moisture. Cotton is sometimes used in fashion applications for its natural feel, but it's less common in functional items because it can shrink slightly when wet. The tape is woven with a specific thread count and density to provide the right balance of strength and flexibility. It needs to be strong enough to hold the teeth firmly even when the zipper is under tension. But it also needs to be flexible enough to curve around your body or fold into a compact space when the garment is stored. The teeth are attached to the tape in different ways depending on the zipper type. In metal zippers, each tooth has a Y-shaped base that's crimped around the edge of the tape, gripping it firmly. In molded plastic zippers, the plastic teeth are formed directly onto the tape during manufacturing, creating a strong integral bond. In coil zippers, the continuous spiral of nylon is sewn into the tape, with each loop secured by the thread that runs along the tape's edge. Now we come to the slider. This is the component that actually operates the zipper, bringing the teeth together or pulling them apart. The slider is a small housing, typically made of metal or durable plastic, that slides up and down the length of the zipper. Inside the slider is where the magic happens. There's a Y-shaped channel that runs through the slider's body. This channel is precisely sized to accommodate the teeth from both sides of the zipper. As the slider moves, the teeth enter this channel at a specific angle, and the shape of the channel guides them together, forcing the projection from one tooth into the hollow of the opposite tooth. The slider has several distinct parts. At the front, there's a narrow opening where the closed teeth emerge. At the back, there are two wider openings where the separate tape strips enter. And in the middle, there's the Y-shaped channel, where the magic of interlocking happens. The walls of this channel are angled just right to guide the teeth into position. They act like a funnel, bringing the two rows of teeth together at the precise angle needed for engagement. The slider also typically includes a mechanism to help it stay in place when you're not moving it. In a locking slider, there's a small internal piece that catches in the teeth when the slider is at rest, preventing it from sliding down on its own. This is why your jacket zipper doesn't unzip itself when you're wearing it. The locking mechanism holds it firmly in place until you deliberately pull on it. Attached to the slider is the pull tab. This is the small handle, often made of metal or tough plastic, that you actually grab to move the slider. The pull tab might be purely functional, or it might be decorative, carrying a brand logo or adding a design element to the garment. Some high-end zippers have elaborate pull tabs made from leather or finished metal, while utilitarian zippers might have simple loops of nylon cord. At each end of the zipper, there are stops. These are small components that prevent the slider from running off the end of the zipper. At the top of the zipper, there are top stops, which are typically small metal or plastic pieces crimped onto the tape just above the last tooth. These catch the slider and prevent it from sliding off the top when you fully close the zipper. At the bottom of the zipper, the arrangement depends on whether the zipper is separating or non-separating. A non-separating zipper, like you'd find on a pouch or a fly front, has a bottom stop at the lower end. This is similar to the top stops, a small piece that prevents the slider from sliding off the bottom. A separating zipper, like you'd find on a jacket, works differently. Instead of a bottom stop, it has a box and pin mechanism. At the bottom of one side of the zipper is an insertion pin, a small piece that slides into the slider when you're closing the zipper. On the other side is a retaining box, also called a starter box, which captures and holds the insertion pin. When you want to close a separating zipper, you first insert the pin into the slider and then into the box. This brings the two sides of the zipper together at the bottom. Then you can pull the slider up, and it will engage the teeth as it goes. These components, the teeth, the tape, the slider, the pull tab, and the stops, work together in a carefully choreographed system. Each component depends on the others. The teeth need the tape to hold them in position. The slider needs the teeth to be shaped just right. The stops need to catch the slider at exactly the right point. When all these components are manufactured with precision and assembled correctly, you get a zipper that works smoothly and reliably, thousands of times over its lifetime. But knowing the components is only the beginning of understanding. The real wonder lies in how they work together, particularly in that Y-shaped channel inside the slider. So let's look more closely at that mechanism now, understanding the gentle physics that makes a zipper lock and unlock with such elegant simplicity. Picture, if you will, a cross-section view of a zipper slider. Imagine we could slice through it vertically and look inside to see its internal structure. What we'd see is that distinctive Y-shaped channel running through the body of the slider. At the back of the slider, the Y has two arms, two separate openings. These are where the two sides of the zipper enter, each with its strip of tape and its row of teeth. The teeth on each side are facing inward toward each other, but they're not yet touching. They're separate, and the zipper is open. As the slider moves forward, which means upward when you're closing a zipper, the two arms of the Y begin to converge. The channel narrows, bringing the two rows of teeth closer together. This is where the interlocking begins. The walls of the Y-shaped channel are angled, creating a wedge effect. As the teeth move through this wedge, they're pushed gently but firmly toward each other. The teeth are slightly offset, remember, so they don't simply ram into each other head-on. Instead, they approach at an angle, with the projection of one tooth sliding towards the hollow of the opposite tooth. The crucial moment comes when the projection and hollow meet. The projection, which is rounded and slightly larger than the hollow, presses against the edge of the hollow. For a fraction of a second, this creates stress. The material of both teeth flexes slightly, elastically, opening the hollow just a tiny bit to accept the projection. This elastic deformation is one of the keys to how zippers work. The teeth are made from materials that can bend slightly without permanently deforming. In metal zippers, this elasticity comes from the physical properties of brass or aluminum. These metals have what's called a yield strength, a point up to which they can be stressed without permanent deformation. Zipper teeth are designed to operate well below this yield strength, so they flex during engagement but spring back to their original shape immediately afterward. In plastic zippers, the elasticity comes from the polymer structure. Nylon and polyester have molecular chains that can slide slightly past each other under stress, then return to their original configuration. This gives plastic teeth a certain springiness that serves the same function as the elasticity in metal teeth. Once the projection seats fully into the hollow, the stress is released. The hollow closes around the projection, and the two teeth are now locked together. This locked configuration is stable. The projection is nestled snugly in the hollow, held in place by the shape of the tooth and the elasticity of the material. And here's the beautiful part. The forces that you might apply to a zipper during normal use pulling outward from the sides or lengthwise along the zipper, cannot unlock this connection. The shape of the teeth means that these forces actually make the lock stronger, not weaker. Pulling outward from the sides just presses the projection more firmly into the hollow. Pulling lengthwise creates tension in the tape, but the teeth themselves remain interlocked. The only force that can unlock the teeth is a very specific one, applied by the slider itself. This happens when you pull the slider downward to open the zipper. At the front of the slider, where the closed teeth emerge, there's a wedge-shaped element. This wedge is pointed and angled precisely. As the slider moves down, this wedge pushes into the gap between two locked teeth. It applies force at just the right angle to pry the projection out of the hollow. The teeth flex again, elastically, as they separate. The projection slides out of the hollow, and the two teeth become independent once more. They emerge from the sides of the Y-shaped channel, each returning to its own side of the zipper. The zipper opens. This entire process happens tooth by tooth in rapid sequence. When you pull the slider up or down, you're not moving all the teeth at once. Instead, you're moving the slider along the zipper, and as it passes each pair of teeth, it either locks them together or unlocks them, one pair at a time. It happens so quickly that it feels instantaneous, but if you could slow it down and watch closely, you'd see a wave of engagement or disengagement rippling along the zipper's length. The forces involved are fascinating to consider. When the slider locks two teeth together, it's applying a force through the wedge action of the Y-shaped channel. This force has to be strong enough to push the teeth together against their natural elasticity. But it can't be so strong that it deforms the teeth permanently or causes them to jam. The design of the channel, its angle and its smoothness, determines exactly how much force is required. Similarly, when the slider unlocks teeth, the wedge at the front must apply enough force to pry them apart, but not so much force that it damages the teeth or makes the slider hard to move. In a well-designed zipper, the force required to operate the slider is low enough that even a child can manage it easily, yet high enough that the zipper feels substantial and secure. Friction plays a role here too. As the slider moves along the zipper, the inner walls of the Y-shaped channel are in contact with the teeth. This creates friction, which can slow the slider's movement and make it feel less smooth. To reduce this friction, zipper manufacturers apply special coatings or lubricants to the teeth or to the inside of the slider. These coatings are typically very thin, just a few molecules thick, but they make a noticeable difference in how smoothly the zipper operates. In some high-quality zippers, the teeth themselves are polished to a smooth finish, reducing friction even further. In others, the slider might have a special low-friction material lining its channel. These refinements, invisible to the casual observer, contribute to the satisfying smoothness of a well-made zipper. The Y-shaped channel is also responsible for maintaining alignment. As the teeth enter the channel, they're guided into exactly the right position for interlocking. If the teeth are slightly misaligned as they approach, the channel corrects this, bringing them into proper registration. This is why a properly functioning zipper can tolerate a small amount of misalignment or tension in the fabric without jamming or failing. However, if the alignment is too far off, or if excessive force is pulling the zipper in the wrong direction, the channel cannot correct it, and the zipper may jam. This is often what happens when you catch fabric in a zipper. The fabric wedges into the channel, preventing the teeth from entering properly, and the whole mechanism seizes up. The slider can't move forward or backward, and you're stuck until you carefully work the fabric free. Understanding this mechanism helps explain why zippers are so reliable when used correctly, and why they fail in the specific ways they do. The elegance of the design lies in its use of geometry and materials science to create a lock and key mechanism that's both strong and reversible. It's a mechanism that Gideon Sundback perfected more than a century ago, and while modern zippers have refinements and improvements, the basic principle remains the same. The Y-shaped channel, the carefully shaped teeth, the elastic properties of the materials, all working together to create a fastener that locks securely but opens smoothly, over and over, reliably. As you lie here, perhaps you can almost feel it. The satisfying click of teeth locking together, the gentle slide of the pull tab, the quiet confidence of knowing that your zipper will hold when you need it to and release when you ask it to. It's a small thing, perhaps, but it's a small thing that works beautifully. Let's turn our attention now to the materials from which zippers are made, because the choice of material affects not just how a zipper looks, but how it behaves, how long it lasts, and what applications it's suitable for. When you look at a zipper, one of the first things you might notice is what it's made from. Is it metal, with a satisfying weight and a bright or brushed finish? Is it plastic, with colorful teeth and a lighter feel? Or is it one of those fine coiled zippers, flexible and almost delicate looking? Each of these types uses different materials, and each has its own characteristics, its own strengths, and its own ideal applications. Let's start with metal zippers, the classic type that's been around since the earliest days of successful zipper manufacturing. Metal zipper teeth are typically made from brass, aluminum, or nickel, though other metals like stainless steel are sometimes used for specialized applications. Brass is perhaps the most common. It's an alloy of copper and zinc, which gives it a warm golden color and excellent mechanical properties. Brass is relatively soft compared to steel, which makes it easy to stamp into shape during manufacturing. But it's also quite strong, with good resistance to wear and corrosion. The process of making brass zipper teeth begins with wire. A coil of brass wire is fed into a specialized machine where it's stamped and formed into the distinctive tooth shape. Each tooth starts as a simple Y-shaped piece. The stem of the Y wraps around the zipper tape, gripping it firmly, while the top of the Y forms the interlocking tooth itself. The machine punches a dimple into one side of the tooth to create the hollow, and leaves a rounded projection on the other side. This stamping process happens incredibly fast in modern zipper factories. A single machine can produce thousands of teeth per minute, each one precisely shaped and positioned. The brass provides enough flexibility that the stamping doesn't crack or damage the metal, but enough spring that the finished teeth have the elasticity needed for reliable interlocking. Brass zippers have several advantages. They're strong and durable, able to withstand significant tension without failing. They have a classic, substantial feel that's appreciated in certain applications like denim jeans or leather jackets. and they're relatively resistant to corrosion, though they can tarnish over time, developing a darker patina that some people find attractive. The drawbacks of brass zippers include their weight. A long brass zipper on a jacket adds noticeable mass. They can also be cold to the touch in winter weather, and they conduct electricity, which might be a concern in certain industrial applications. Additionally, brass contains copper, which can sometimes react with certain dyes or chemicals in fabrics, causing discoloration. Aluminum offers an alternative to brass. Aluminum zippers are lighter, sometimes significantly so. Aluminum is less dense than brass, which means an aluminum zipper of the same size will weigh less. This makes aluminum attractive for applications where weight matters, such as outdoor gear or luggage that might need to meet airline weight restrictions. Aluminum also has a silver-white color rather than brass's gold, which gives it a different aesthetic. It can be anodized to create different colors or finishes, from bright shiny silver to matte black to vibrant reds and blues. This versatility makes aluminum popular in fashion applications. The manufacturing process for aluminum zippers is similar to brass, involving stamping and forming from wire. However, aluminum requires slightly different handling because it's softer and more prone to deformation during manufacturing. YKK, one of the world's largest zipper manufacturers, developed a special aluminum alloy called 56S specifically for zippers. This alloy has improved strength and formability compared to standard aluminum, making it ideal for zipper manufacturing. Nickel is another metal used in zippers, though less commonly than brass or aluminum. Nickel provides a bright silver finish similar to aluminum, but with different properties. It's harder than brass, which makes it more resistant to wear, but also more difficult to form during manufacturing. Nickel zippers are sometimes used in applications requiring exceptional durability, or simply for their distinctive bright silver appearance. And one important note about nickel is that some people have nickel allergies. For individuals with this allergy, wearing a garment with a nickel zipper in direct contact with skin can cause irritation or dermatitis. This has led many manufacturers to use nickel-free alternatives or to apply protective coatings over nickel zippers. Stainless steel is occasionally used for zippers in very specialized applications. Stainless steel is extremely strong and highly resistant to corrosion, making it ideal for zippers that will be exposed to harsh environments, salt water, or aggressive chemicals. However, stainless steel is expensive and challenging to work with, so it's reserved for applications where its properties are truly needed, such as in marine equipment or certain industrial uses. Metal zippers, regardless of the specific metal, share certain characteristics. They're rigid compared to plastic zippers, which means they work best in straight applications rather than curved seams. They make a distinctive metallic sound as they open and close. They're relatively heavy, and they have a classic, premium feel that many people associate with quality. Now, let's turn to plastic zippers, which have become increasingly common since their development in the mid-20th century. Plastic zipper teeth are typically made from polyacetal, also called POM, polyester or nylon. These synthetic polymers offer different properties than metal, properties that make them advantageous in many applications. Polyacetal is one of the most common materials for molded plastic zippers. It's an engineering plastic, meaning it has mechanical properties good enough for functional parts, not just decorative ones. Polyacetal is strong, with good resistance to wear and chemicals. It's dimensionally stable, meaning it doesn't shrink or expand much with temperature changes. And it can be molded into precise shapes with excellent detail. In a molded plastic zipper, each tooth is injection molded directly onto the zipper tape. The manufacturing process involves heating polyacetal until it's molten, then injecting it into a mold that's shaped like a zipper tooth. The tape runs through the mold, and as the plastic cools and hardens, it bonds to the tape, creating a strong connection between tooth and tape. This molding process allows for interesting tooth designs. Plastic teeth can be shaped in ways that would be difficult or impossible with stamped metal. They can have complex interlocking features, gradual curves, and even built-in flexibility. Manufacturers can adjust the thickness, width, and profile of the teeth to optimize them for specific applications. Plastic zippers have several key advantages. They're lightweight, significantly lighter than metal zippers of comparable size. They're resistant to corrosion, making them ideal for outdoor applications where they might be exposed to rain or humidity. They can be made in virtually any color, either by dyeing the plastic or by using colored plastic pellets in the molding process. They're non-conductive, which is important in some industrial and electronic applications, and they're often smoother and quieter to operate than metal zippers. The main drawback of plastic zippers is that they're not quite as strong as metal zippers. While a plastic zipper is plenty strong for most applications, if you need maximum tensile strength, metal is still the better choice. Plastic teeth can also be more prone to damage from sharp impacts. If something strikes the teeth hard enough, they might crack or chip, whereas metal teeth would be more likely to bend but remain functional. Nylon and polyester are also used in zipper manufacturing, particularly for coil zippers. In a coil zipper, instead of individual teeth, the zipper uses a continuous spiral of nylon or polyester monofilament. This spiral is sewn into the zipper tape, with each coil of the spiral forming one tooth equivalent. The manufacturing of coil zippers is quite different from metal or molded plastic zippers. It begins with extruding a plastic monofilament, a thin plastic wire. This filament is then heated and formed into a spiral shape by winding it around a mandrel or through a series of heated screws. The resulting spiral has a specific size and pitch, with each loop spaced at exactly the right distance to interlock with the coils from the opposite side. Once the spiral is formed, it's sewn onto the zipper tape using a special sewing machine. The thread that holds the spiral to the tape runs through the center of each coil, securing it firmly. The result is a flexible, smooth zipper where the teeth are not discrete pieces, but rather a continuous spiral. Coil zippers have unique properties. They're extremely flexible, able to curve smoothly around corners or follow complex seams. This makes them ideal for garments that need to fit closely to the body, or for bags with curved openings. The continuous coil also means there are no gaps between teeth that could catch on fabric or allow water to seep through. The weight of a coil zipper is very low. The thin plastic monofilament uses much less material than metal teeth or molded plastic teeth, resulting in an exceptionally lightweight fastener. This is prized in applications like ultra-light hiking gear, where every gram matters. Coil zippers are also incredibly smooth to operate. Because the coils are rounded and uniform, and because the material is relatively soft, the slider glides along with minimal friction. This smoothness is appreciated in high-quality garments, where the ease of operation contributes to the overall user experience. The main limitation of coil zippers is their tensile strength. While adequate for most uses, coil zippers can't match the sheer pulling strength of a robust metal zipper. They're also more susceptible to damage from heat. If you were to accidentally iron over a coil zipper, the plastic could melt or deform. Metal zippers would be unaffected by such treatment. The zipper tape itself is typically made from woven fabric, as mentioned earlier. Cotton provides natural fibers with a soft hand feel, but it can shrink when washed and may weaken over time with exposure to moisture and UV light. Polyester is more dimensionally stable, doesn't shrink, and has excellent resistance to degradation from sun or water. Nylon offers high strength and excellent durability, though it can be more expensive than polyester. Some specialized zippers use even more exotic materials. Heavy-duty industrial zippers might use aramid fiber tapes, the same type of fiber used in bulletproof vests for exceptional strength. Marine zippers might use polyurethane-coated tapes that are completely waterproof. Zippers for flame-resistant clothing might use inherently fire-resistant fibers like Nomex or Kevlar. The choice of material for a zipper isn't arbitrary. It depends on the application, the environment the zipper will be used in, the aesthetic desired, and the budget available. A denim jean manufacturer might choose a brass zipper for its classic look and robust strength. An outdoor gear company might select an aluminum or coil zipper for weight savings. A fashion designer might opt for a brightly colored molded plastic zipper as a design element. Understanding these materials helps us appreciate that a zipper isn't just a zipper. It's a carefully selected combination of materials, each chosen for specific properties, all working together to create a fastener suited to its intended use. And now, having explored the materials, let's journey into the factories where these materials are transformed into the millions of zippers that the world uses every day. Let's watch in our minds as wire becomes teeth, as plastic becomes coils, as tape and teeth are brought together into finished zippers. Imagine a factory floor, a large, well-lit space filled with specialized machines. The air carries a faint metallic scent from the wire being processed, mixed with the slightly sweet smell of molten plastic from the molding machines. There's a rhythm to the place, a constant hum of machinery running at precise speeds, each machine playing its part in the complex choreography of zipper manufacturing. Let's start with metal zippers, following the process from raw wire to finished product. Coils of brass or aluminum wire arrive at the factory, each coil containing hundreds or thousands of meters of wire. This wire has been drawn at a metal mill, pulled through progressively smaller dies until it's exactly the right diameter for zipper teeth. The wire is usually fairly soft at this stage, which will make it easier to stamp and form. The wire is loaded onto the first machine, a straightener that removes any curves or kinks from the coiled wire, producing a perfectly straight length. From there, the wire feeds into a rolling mill. This machine passes the wire between two rotating rollers that are precisely profiled. As the wire passes through, it's shaped from a round cross-section into a Y shape. The stem of the Y will eventually grip the tape, while the top will form the tooth. This Y-shaped wire then moves to the stamping machine, and here's where the magic happens. The stamping machine is a marvel of precision engineering. It has dies, hardened steel molds, that come together rapidly, hundreds or even thousands of times per minute. As the Y-shaped wire passes through, the machine performs several operations in sequence. First, a punch creates a dimple on one side of the wire. This dimple, or cup, will be the hollow that accepts the projection from the opposite tooth. The punch presses into the metal, deforming it plastically, creating a small depression. Almost simultaneously, another part of the machine cuts the wire, separating one tooth from the continuous wire. The cut happens at just the right spot, leaving the tooth the correct length. Next, the machine bends the stem of the Y into shape. The two legs of the Y are crimped around the edge of the zipper tape, which has been fed into the machine from a separate roll. The crimping is firm enough to hold the tooth securely, but not so tight that it damages the tape fibers. All of this happens in a fraction of a second. The tooth is formed, cut, and attached to the tape in one smooth, continuous motion. The result emerges from the machine as a stringer, which is what manufacturers call one side of a zipper, the tape with its row of teeth attached. The machine produces two stringers simultaneously, one for each side of the zipper. The teeth on these two stringers are carefully positioned so that they'll offset correctly when the zipper is closed. Getting this alignment right is crucial. If the teeth are even slightly misaligned, the zipper won't close properly. After the stringers come off the stamping machine, they may go through additional processing. A wire brush might scrub the teeth to remove any burrs or rough edges left by the stamping process. The stringers might be painted or coated, either for corrosion protection or to match the color of the garment they'll be sewn into. The stringers are then pressed together temporarily using a special tool similar to a slider. This allows quality control inspectors to check that the teeth engage properly. They're looking for smooth operation, secure locking, and consistent tension along the length of the zipper. Next, the tape portion of the stringers might be starched to give it more body and make it easier to sew. The stringers are then ready to be cut to length and have their stops and sliders attached. For a non-separating zipper, bottom stops are crimped onto the tape at the bottom of the stringers, and top stops at the top. A slider is then threaded onto the interlocked teeth from the bottom, and a pull tab is attached to the slider. For a separating zipper, an insertion pin is attached to the bottom of one stringer and a retaining box to the other. Top stops are added. The slider is attached, typically by temporarily separating the teeth at the top, inserting the slider, and then re-engaging the teeth above it. The finished zippers are then packaged, often in bundles of similar sizes, and shipped to clothing manufacturers, bag makers, tent manufacturers, or directly to fabric stores for home sewers. Now, let's look at plastic zipper manufacturing, which follows a somewhat different path. For molded plastic zippers, the process begins with plastic pellets. These might be polyacetal, polyester, or nylon pellets, depending on the type of zipper being made. The pellets are loaded into a hopper on an injection molding machine. Inside the machine, the pellets are heated until they melt into a thick, viscous liquid. This molten plastic is then injected into a mold under high pressure. The mold is shaped like a zipper tooth, with cavities that form the detailed features of the tooth, including the interlocking projection and hollow. The zipper tape is fed through the mold continuously. As the molten plastic is injected, it flows around the tape, bonding to it as it cools and solidifies. The result is a tooth that's integrally molded onto the tape, forming a very strong connection. Modern injection molding machines can form multiple teeth simultaneously, with the tape advancing incrementally between each injection. This allows for high production speeds, with completed stringers emerging from the machine at rates of several meters per minute. The molded stringers may then be processed further. They might be dyed if color is required, or coated if special properties like water resistance are needed. Like metal stringers, they're inspected, cut to length, and have their stops and sliders attached. Coil zippers follow yet another manufacturing process, one that's particularly elegant in its simplicity. The process begins with extruding a plastic monofilament. Plastic pellets are melted and forced through a circular die, emerging as a thin plastic wire. This wire is cooled rapidly, usually with air or water, to solidify it while maintaining flexibility. The solidified monofilament is then fed into a coiling machine. This machine has heated screws, or a heated mandrel that forms the monofilament into a spiral. As the monofilament passes through, it's heated just enough to become pliable, then wrapped into a coil shape. The coil is cooled again immediately to set its shape. Some coiling machines make 2 coils simultaneously, one for each side of the zipper, with the coils pre-interlocked. Others make each coil separately, requiring them to be joined later. The finished coils are then sewn onto zipper tape using specialized sewing machines. These machines position the coil precisely along the edge of the tape and stitch through the center of each coil, securing it firmly. The sewing thread runs through every loop of the coil, ensuring that the coil can't separate from the tape. Once sewn, the coil stringers are processed similarly to other zipper types, with cutting, stop attachment, and slider installation. Throughout all these manufacturing processes, quality control is constant and rigorous. Automated systems might inspect every tooth for correct dimensions, checking that they're all the same size and shape. Tension tests might be performed on sample zippers, pulling them apart to ensure they meet strength specifications. Operation tests cycle the sliders up and down thousands of times to verify smooth, reliable performance. The tolerances in zipper manufacturing are surprisingly tight. A tooth that's even a fraction of a millimeter too large or too small can cause problems. The spacing between teeth must be consistent within very small margins. The alignment of teeth on opposite stringers must be precise. These tolerances are maintained through careful machine calibration, high-quality tooling, and constant monitoring. Modern zipper factories are highly automated, with machines handling most of the repetitive tasks. But skilled technicians are still essential. They set up the machines, adjust the parameters, monitor the quality, and troubleshoot problems when they arise. Making zippers reliably requires both sophisticated technology and human expertise. The result of all this effort is something that seems simple, something that costs just pennies to manufacture, but something that works reliably in billions of applications around the world. A zipper that will open and close thousands of times over its lifetime, that will hold securely when needed, that will require almost no maintenance or thought from its user. It's a testament to the power of good design combined with precision manufacturing. And it's a reminder that sometimes the most valuable inventions are the ones we barely notice, the ones that fade into the background of our daily lives, working quietly and reliably. From the factory, these zippers travel to clothing manufacturers, to outdoor gear companies, to bag makers and tent factories. There, they're sewn into products that will be used and appreciated by people all over the world. But not all zippers are created equal, and for different applications, different types of zippers are required. Let's explore these variations now. Not all zippers are the same, and as zipper technology has evolved, manufacturers have developed specialized types for different applications. Some zippers need to be waterproof, others need to be invisible. Some need to be exceptionally strong, others need to be as lightweight as possible. Let's explore these different variations, understanding what makes each one special. First, let's distinguish between separating and non-separating zippers, a fundamental division in the zipper world. A non-separating zipper is what you'd find on a bag, a pouch, or the fly front of a pair of pants. In this type, the two sides of the zipper are permanently joined at the bottom. The slider can move up to close the zipper and down to open it, but the two sides never completely separate from each other. This design is simpler and usually less expensive, and it's perfectly adequate for applications where you don't need to fully separate the two sides. A separating zipper, on the other hand, is what you'd find on a jacket or a sleeping bag. This type allows the two sides to come completely apart. At the bottom, instead of a permanent connection, there's a box and pin mechanism. To close a separating zipper, you first insert the pin into the box, bringing the two sides together at the bottom. Then you pull the slider up to engage the teeth. To open it fully, you pull the slider down to the bottom, and then you can pull the pin out of the box, completely separating the two sides. Separating zippers are more complex to manufacture and typically cost more, but they're essential for garments that need to be put on and taken off, like jackets and vests. Within these broad categories, there are many specialized variations. Let's look at some of the most interesting. Invisible zippers are designed to be, well, invisible. In a normal zipper, the teeth are visible on the front of the garment, creating a visual line. In an invisible zipper, the teeth are hidden behind the zipper tape. When the zipper is closed, you see only a thin seam line that looks like any other seam in the garment. This is achieved through clever design. The teeth of an invisible zipper are behind the tape, rather than along its edge. The coils face backward, and the tape is folded over them. When sewn into a garment, the tape sits flush with the fabric on both sides, and the teeth are completely hidden in the seam allowance. Only the slider pull is visible at the top. Invisible zippers are popular in dresses, skirts, and other garments where the designer wants a clean, uninterrupted line. They're typically coil zippers because the flexible coil can be easily hidden behind the tape. Two-way zippers have two sliders on the same zipper. This allows the zipper to be opened from either the top or the bottom. You might find these on long jackets or coats. The dual slider design lets you unzip the bottom of a coat while keeping the top closed, giving you more freedom of movement when sitting or driving, or simply allowing for better ventilation. Two-way zippers are a bit more complex to manufacture and use, but they're very practical for certain applications. Outdoor gear, especially jackets for skiing or hiking, often uses two-way zippers for this reason. Waterproof and water-resistant zippers represent another important category, especially for outdoor gear, marine equipment, and protective clothing. A standard zipper, even when closed, is not watertight. Water can seep between the teeth, through the gap where the slider sits, or along the tape. For most applications, this doesn't matter. But for a diving suit, a rain jacket, or a waterproof bag, it's crucial. Water-resistant zippers, like YKK's AquaGuard line, are coil zippers that have been specially treated. The tape is coated with a polyurethane film on one side and treated with a durable water repellent, now DWR coating, on the other. The polyurethane film creates a barrier that water cannot easily penetrate, while the DWR coating causes water to bead up and roll off the surface. These zippers aren't perfectly waterproof, but they're highly water-resistant, suitable for rain jackets, bags, and similar applications where some moisture protection is needed, but total waterproofing isn't critical. True waterproof zippers go a step further. YKK's AquaSeal and ProSeal zippers are examples. These use special tooth designs with gaskets that create a watertight seal between the teeth. When closed, these zippers can withstand significant water pressure without leaking. They're used in diving suits, dry suits, waterproof bags, and industrial applications where moisture absolutely cannot penetrate. The engineering of waterproof zippers is sophisticated. The teeth have to interlock in a way that not only provides mechanical strength but also creates a compressed seal. Special materials are used that remain flexible and seal-worthy even when exposed to salt water, chemicals, or repeated compression. Waterproof zippers are more expensive and slightly stiffer than standard zippers, but for certain applications, they're indispensable. Heavy-duty industrial zippers take strength and durability to another level. These might be used in inflatable boats, heavy canvas tarps, truck covers, or industrial safety equipment. They feature larger teeth, thicker tape, and robust sliders designed to withstand harsh treatment. Some heavy-duty zippers use especially large metal teeth with sizes that can be an inch or more across when closed. Others use specialized materials like flame-resistant fibers for applications where fire safety is critical. The sliders might be oversized and easy to grip, even when wearing heavy gloves. Testing for these zippers is rigorous. They might be cycled tens of thousands of times to verify durability. They might be subjected to extreme temperatures, from deep freeze to high heat. They might be pulled with forces measured in hundreds of pounds to test their tensile strength. Zipper sizes are designated by numbers, typically ranging from 3 to 10, with larger numbers indicating larger teeth. A number 3 zipper is delicate and lightweight, suitable for lightweight garments or fine fabrics. A number 5 is medium weight, the most common size for general purpose use. A number 10 is heavy duty, used for outdoor gear, luggage, and heavy garments. Some specialized applications use even larger sizes, with number 15 or larger zippers appearing in industrial contexts. Conversely, some ultra-lightweight applications use number 2 or even smaller zippers, though these are less common. The variety of zippers available is truly remarkable. Pick up any catalog from a zipper manufacturer and you'll find hundreds or thousands of different configurations. Different sizes, different materials, different colors, different tooth designs, different tape widths, different slider styles. This variety exists because zippers are used in so many different applications, each with its own requirements. A sleeping bag manufacturer needs a zipper that's smooth and snag-free, that works reliably even when operated in the dark by someone who's half asleep. A tent manufacturer needs a zipper that will work in rain and cold, that won't freeze or stick, that can be opened and closed with one hand. A designer creating an evening gown needs a zipper that's nearly invisible, that won't catch on delicate fabric, that moves smoothly and quietly. Each of these applications drives innovation in zipper design. Manufacturers are constantly developing new variations, new materials, new features to meet the evolving needs of their customers. And through all this innovation, the fundamental principle remains the same. Interlocking teeth, operated by a slider, joining two pieces of fabric together reliably and reversibly. As we near the end of our journey through the world of zippers, there's one more story worth telling. The story of a company that has come to dominate zipper manufacturing worldwide, a company whose initials appear on zippers you likely use every day. Let's talk about YKKK. If you've ever looked closely at a zipper on your jacket or bag, you might have noticed 3 letters embossed on the slider. YKK. These initials are ubiquitous in the zipper world. It's estimated that YKK produces nearly half of all zippers made globally, billions upon billions of zippers every year. But who is YKKK? And how did they come to dominate this market so thoroughly? YKK stands for Yoshida Kogyo Kabushiki Kaisha, which translates to Yoshida Manufacturing Corporation. The company was founded in 1934 by Tadao Yoshida in Tokyo, Japan. At the time, zippers were relatively new, having only been perfected a couple decades earlier. The Japanese textile industry was growing rapidly, and there was increasing demand for quality fasteners. Yoshida started small, very small. His company initially just bought zippers from other manufacturers and sold them to clothing makers. But Yoshida was dissatisfied with the quality of the zippers available. They broke too easily. They didn't close smoothly. He knew they could be better. So Yoshida decided to manufacture zippers himself. He didn't just want to make zippers, though. He wanted to make the best zippers possible, and he wanted to control every aspect of their production to ensure quality. This led to a philosophy that would define YKK for decades to come: vertical integration. Rather than buying components from suppliers, YKK would make everything themselves. They would smelt their own brass from raw copper and zinc. They would weave their own zipper tape. They would design and build their own manufacturing machines. This gave them complete control over quality and allowed them to innovate in ways that wouldn't be possible if they were dependent on outside suppliers. In the years after World War II, as Japan rebuilt and its economy grew, YKK grew with it. Yoshida invested heavily in research and development, constantly working to improve zipper design and manufacturing processes. YKK developed new alloys for zipper teeth, new weaving patterns for tape, new slider designs for smoother operation. But Yoshida's ambitions weren't limited to Japan. In the 1950s and 60s, he began expanding internationally. YKK opened factories in New Zealand, Australia, the United States, and Europe. And here's what was remarkable. These weren't just assembly plants buying parts from Japan. They were fully integrated manufacturing facilities, each one capable of producing complete zippers from raw materials. This global expansion strategy was unusual and capital-intensive. It would have been much cheaper to manufacture everything in Japan and export finished zippers. But Yoshida believed in a philosophy he called the cycle of goodness. The idea was that YKK should contribute to the prosperity of the countries where it operated. By manufacturing locally, YKK provided jobs, paid local taxes, and integrated into local economies. In return, those communities would support YKK, and everyone would prosper. This philosophy wasn't just altruism, it was also smart business. By manufacturing locally, YKK could avoid import tariffs, reduce shipping costs, and respond more quickly to local market demands. A clothing manufacturer in the United States could order YKK zippers and receive them quickly from a nearby YKK factory with the same quality standards as zippers made in Japan or anywhere else in the world. By the 1970s, YKK was the largest zipper manufacturer in the world, and they've maintained that position ever since. Today, YKK operates more than 110 facilities in over 70 countries. They employ over 40,000 people worldwide, and they produce not just zippers, but a wide range of fastening products including snap fasteners, hook and loop fasteners, buckles, and buttons. YKK's commitment to quality is legendary in the industry. They test their zippers extensively, far beyond what most competitors do. Zippers are cycled open and closed tens of thousands of times to verify durability. They're subjected to tension tests, corrosion tests, temperature cycling, UV exposure, and more. They measure dimensions down to fractions of a millimeter to ensure consistency. This obsessive attention to quality has made YKK the preferred supplier for major brands worldwide. If you buy clothing or gear from well-known brands, chances are very good that the zippers are YKK. The company doesn't advertise much to consumers. They don't need to. Their reputation among manufacturers speaks for itself. YKK also continues to innovate. They've developed water-resistant coatings, specialized sliders, ultra-lightweight materials, and numerous other advances. They hold thousands of patents related to zipper technology. They employ materials scientists, mechanical engineers, and chemists who continuously work to improve their products. One interesting aspect of YKK is their decision to mark their zippers with the YKK logo. That tiny embossed text on the slider serves multiple purposes. It identifies the manufacturer, which is useful for quality assurance. It signals quality to consumers who recognize the brand. And it makes counterfeiting more difficult, a real concern in the fastener industry. There are, of course, other zipper manufacturers. Companies like SBS in China, Ryrie in Switzerland, and various smaller manufacturers around the world all produce zippers. Some of these specialize in particular niches, like luxury fashion or extreme performance applications. But YKK's combination of global reach, consistent quality, and vertical integration makes them dominant in the market. For consumers, this dominance is generally positive. It means that no matter where in the world a garment is manufactured, it can easily source reliable, standardized zippers. It means that replacement zippers and sliders are widely available. And it means that the humble zipper, something we interact with multiple times every day, is remarkably reliable. As you lie here, perhaps drifting toward sleep, you might think about all the zippers you've used today. The one on your jacket as you left the house, the one on your bag or backpack, the one on your pants. Each of those zippers is the product of over a century of innovation, from Whitcomb Judson's early struggles to Gideon Sundback's breakthrough to Tadao Yoshida's commitment to quality. Each one is a small marvel of engineering, designed to work perfectly thousands of times without thought or effort. And each time you pull a zipper closed, feeling that satisfying sequence of teeth clicking into place, you're experiencing the result of careful thought about tooth geometry, material properties, and manufacturing precision. You're using a piece of technology that has been refined over generations to be simple, reliable, and nearly invisible in its competence. And so our gentle journey through the world of zippers comes to a close. We've traveled from the button-filled world of the 19th century to the modern day, where billions of zippers quietly serve us every day. We've met inventors who dreamed of easier ways to fasten things, and we've seen how those dreams evolved into reality through patience, ingenuity, and countless small improvements. We've looked closely at the anatomy of a zipper, understanding how teeth and tape and slider work together in careful harmony. We've marveled at the Y-shaped channel, that simple yet elegant mechanism that locks teeth together securely, but releases them smoothly with just a gentle pull. We've explored the materials from which zippers are made, from gleaming brass to flexible nylon, each chosen for its specific properties. We've visited, in our minds, the factories where zippers are manufactured, watching as wire becomes teeth and plastic becomes coils, as millions of zippers take shape through the precise dance of automated machines. We've learned about the different types of zippers, each specialized for particular applications, from invisible zippers that hide in garments to waterproof zippers that seal out moisture. And we've met YKK, the company that produces nearly half the world's zippers, a company built on a philosophy of quality, vertical integration, and contribution to the communities where it operates. Through all of this, a theme emerges. The zipper is a testament to the power of good engineering applied to everyday problems. It's not flashy. It's not the kind of technology that gets celebrated in headlines or wins prestigious awards. But it's the kind of technology that makes modern life possible, that makes our daily routines smoother and easier in ways we rarely stop to appreciate. Think about a world without zippers. Think about fumbling with dozens of tiny buttons every time you wanted to put on or take off a jacket. Think about the inconvenience, the wasted time, the frustration. The zipper eliminated all of that, replacing it with a single smooth motion. And it did so with such elegance and reliability that we barely notice it. It has become background technology, something we only think about when it breaks, which, with a good zipper, almost never happens. There's something beautiful about that. Something beautiful about technology that serves us quietly, that asks nothing of us, that simply works. The zipper represents a kind of perfection in design, where form and function come together so seamlessly that the technology seems almost natural, almost inevitable, as if it had always existed. But it didn't always exist. Someone had to imagine it. Someone had to struggle and fail and try again until they got it right. Someone had to think about tooth geometry and slider channels and tape weaving and all the countless details that make a zipper work. And then manufacturers had to figure out how to make millions of them reliably and affordably. All of that effort, all of that ingenuity, went into creating something that we now take completely for granted. Perhaps that's the highest compliment that can be paid to an invention. Not that it's impressive or remarkable, but that it fades into the background of our lives, that it becomes so natural and reliable that we forget it's even there. The zipper has achieved that. It has become invisible, not in the way an invisible zipper is literally hidden, but in the way that perfectly functional technology becomes invisible. We don't think about it. We just use it. And it works. As you settle deeper into rest now, as your breathing slows and your thoughts begin to drift, perhaps you'll carry with you a new appreciation for this small but remarkable invention. Perhaps tomorrow, when you pull a zipper closed, you'll think for just a moment about all that went into making that simple action possible. You'll feel the teeth clicking together, one after another, and you'll know that behind that simple motion is a century of innovation. You'll know that the metal or plastic teeth are shaped just so, designed to lock together securely but separate smoothly. You'll know that inside the slider is a Y-shaped channel, guiding those teeth together with carefully calculated forces. You'll know that the tape holding everything together was woven to precise specifications, balancing strength and flexibility. You'll know that the whole assembly was manufactured with incredible precision, with tolerances measured in fractions of millimeters. And you'll know that this small marvel of engineering will work reliably, day after day, year after year, thousands of times over its lifetime, asking nothing from you but an occasional gentle pull. If you're still awake and you enjoyed learning about how zippers work, consider subscribing to hear more peaceful journeys through the technology around us. There are so many everyday things worth understanding, so many small marvels hiding in plain sight. But for now, rest well. Let your muscles relax, let your mind quiet, and drift off to sleep knowing just a little bit more about the ingenious world we live in. Sweet dreams, and may all your zippers glide smoothly.